Hello friends, welcome to engineering tutorial. So we will continue our discussion with television engineering, and so far we have discussed various introductory concepts related to the transmission and reception. First we discussed that the basic in a quick way about the basic concepts related to transmission and reception of TV signals. The audio and the video, and then we discussed the various characteristics related to image or the picture frame, where we discussed about the aspect ratio, the brightness, contrast, then the color characteristics, all of that. So in this video we are going to discuss about the concept of scanning and synchronization in TV. In the first video, the TV transmission and reception, we just came across this block diagram for the transmitter side and the receiver side. Here we came across this block, scanning and synchronizing circuit at the transmitter side, which is connected to the TV camera, the video section, and at the receiver side this synchronization and detecting circuit. So the scanning and synchronization, this term is common at both the transmitting and receiving sides. So in this video we are just going to have a basic idea, we're just going to get a basic idea of what scanning is. There are a lot of things associated with it. So scanning essentially is the procedure by which the image which is captured by the camera, the optical image, the frame, it is divided into many small picture elements, rectangular picture elements, very small picture elements, and these small picture elements are called as pixels. We have already discussed in the transmission and the receiving section, TV transmission reception, that whatever image is formed, whatever frame or image is formed, it cannot be transmitted as whole, as in its entirety. We have to break it down into small elements, each element corresponding or representing a certain amount of brightness level, contrast level, color, the wavelength. It will be represented by certain voltage or current signals, and this process of converting the entire image, the picture frame, into small picture elements having different color characteristics, brightness characteristics, tonal gradation, color, everything that represents a picture element or pixel, and this process is called as scanning, breaking down of an image into small picture elements, a big picture into small picture elements. For example, let's say this is the image or picture which is to be transmitted. We cannot send it as a whole, we have to break it down into small picture elements. These small squares, they represent the small picture elements. Now it is represented here, the squares are prominent, we can make it out that the squares, they are visible, but in actual they are so small that it is very difficult to pinpoint that whether it is a square. They will appear as small dots. Okay, so here, just to illustrate how the pixelation takes place, I have just drawn it as big squares, not very big squares, just so that you can have an idea of what happens in the scanning process. So scanning is of two types. First one is progressive scanning, and the second one is interlaced scanning. So we'll discuss them one by one in a quick way. So before discussing progressive and interlace scanning, essentially the process of scanning is just like reading a book. When we read a book or a newspaper or any reading material, we start from the left, read one line or one, complete first row, whatever this, from left to right. Then we go to the next line, go one line down, again from left to right, again we go one line down, left to right, and then we gradually move from top to bottom, extreme right. That completes one page of the book, reading one page of the book. Line by line, from left to right, we move from top to bottom. So scanning is also like that. Here what the eye does, human eye does in reading, here it is done by an electron beam. Okay, an electron beam, it scans an image or breaks down an image row by row, line by line, from top to bottom into small picture elements. Okay, so basically the image frame is divided into horizontal strips, horizontal lines, very many small horizontal lines. It is broken down into small picture elements, line by line, from left to right, top to bottom, and then it is converted into picture elements. Now it is done by the application of sawtooth waves to the horizontal and vertical deflection plates of the camera tube. Okay, so we will discuss about the design of the TV camera, the internal circuitry. That's why I said there are a lot of things associated with this, so we are not going to discuss all of that here. We will discuss it in the transducer section, the TV transducers. So there are a lot of things associated with. Here we are just going to discuss about the basic concept, the basic idea about what scanning is. So scanning, the progressive scanning, just like I said, the direct scanning, it is also called as direct scanning. Like I said, it is equivalent to the process of reading a book. So what happens that we have this image frame, whatever picture is captured by the camera. The electron beam, it starts from the extreme left at the top. Then it moves like this, gradually, a slight oblique slant there is. It moves from left to right, not straight, okay, not perfectly straight, but little bit slantingly. Okay, then it moves from left to right, completes one line. Then again it returns back to this spot in straight horizontal path from right to left. This is slant. The blue line, it represents the scanning beam. Okay, then the red, which returns back, which represents the returning back of this electron beam back to the left to scan the next line, this is called as retrace. Okay, this is called as retrace. Again, it reaches here, the electron beam, the next line is scanned, it is broken down into small picture elements in a slightly slanting way. Again it returns back here, again scanning takes place, again it returns back here, again scanning takes place again, and then like this the whole frame is broken down into small picture elements. After it reaches here, this spot, one complete frame is complete. Okay, the electron beam directly moves to its original position, the starting position. Okay, so this is called as the vertical retrace. It is not exactly moving straight in a vertical way. Again, it's a slightly slantingly, diagonally it is moving. Still it is called as vertical retrace in progressive scanning. So it is similar to the process of reading a book, but in book we read it in straight horizontal movement, but here you see it is looking like slanting in this manner, because here the width, the distance between these lines, just to make you understand, I have taken this width as very little bit more, but in actual the distance between these lines is very small, very small. It does not appear as if it is slant, it appears straight ahead, because the gap between this line and this line, it is very small, very small. That's why it appears as if it is moving straight. But here, just to make you understand, I have kept a little bit gap between lines. That's why it is looking like it is moving in slantingly way. Okay, so this is progressive scanning. So it is done by a sawtooth waveform. So this blue line, it represents the trace or the scanning of the electron beam, and this red line, it represents the retrace path. Okay, the voltage variation during trace or the scanning period and the retrace period. This is the time period of the trace or the scan, and this is the retrace time period. Obviously the scanning period is more than the retrace period. Okay, so here the blue represents the scanning electron beam, the red horizontal, it is the retrace of the electron beam, and then the movement at the extreme right at the bottom to the extreme left at the top to its initial position, that is the vertical retrace of the electron beam. Now when one complete frame is scanned, from extreme left at the top to the bottom right, that corresponds to one complete image being scanned by the transmitter, and that sends that one complete frame to the receiver. Okay, and it is done so fast that it appears as if there is no gap in between them. Okay, so here the important thing is how many scanning lines are there. Okay, the number of scanning lines. So the different TV systems they have different scanning lines which is adopted in various countries. So it can have values for 405, 525, 625, 819. So you see how many number of lines, scanning lines are there in one frame. So as I said, the number of scanning lines are so large that the gap between them is very small. So this slant movement of the electron beam, it is hardly recognizable. It is hardly visible as a slant. It appears as it is moving straight in straight horizontal paths. So this is the progressive scanning. Now we'll discuss about the interlace scanning. So one of the problems of progressive scanning is it produces a certain flicking effect. Okay, when there is a transition, during the retrace period, because of some mismatch between the frame repetition frequency and the power supply frequency, it causes a certain flicking effect. Okay, the transition of brightness from dark to bright. We have already discussed about that in the intensity, that video. You can check out that video. The persistence of vision, all of this comes into play. So because of that, because of some mismatch between the frame repetition frequency and the power supply frequency, because of that there is a flicking effect is produced, which is very which is not good for viewing. When we are seeing a movie, slight variation between bright and dark, as if a strip of black gray region appears on the screen. So that is not so good. So in order to counter the problem of this flicking effect, interlace scanning is used. So what is done in interlace scanning? The picture frame, whatever frame we are taking, it is divided into two groups, two fields. Okay, just like this. The entire picture frame, it is divided into two fields, and the picture frame consisting of the scanning lines, it is shown twice. It is repeated twice, and each field, it contains half of the scanning lines, the even field and the odd field. Okay, odd field contains half of the scanning lines, the even field consists of half of the scanning lines. So here the scanning takes place in this way. It starts from the extreme left at the top. It starts from A here. It moves from here to here. Again the retrace, the red portion, the red arrowhead. Again it moves from here to here. Retrace here to here. Retrace, scan, retrace until it reaches B. So one half portion of the frame is scanned. Again it moves from B to C. Straight ahead, top, vertical retrace. After reaching C, again the same process is repeated. From C, it starts from here, the electron beam scans, reaches here, then retrace, horizontal retrace marked by the red arrowhead. Again it reaches, starts from here to here until it reaches D. So one complete frame is scanned. So let us understand how it happens. So in progressive scanning, the picture frame is scanned once, okay, at one go. The electron beam scans the picture frame at one go, just like this. Each picture frame is divided into scanning lines and all the lines are scanned at once, just like this, okay. But what happens in the interlace scanning? Let's say this picture, it is divided into two fields which are the even and odd fields, they lie in between. So if you take this picture, it is divided into even and odd scanning lines. See, this portion at the top here, this is the top portion. Just below it, the portion, it is in the odd field. See, one is in the even field at the top. Then just below the frame below, the portion of the frame below, it is in the even field. Again the portion below, it is in the odd field, 3. Again the portion below it, it is in the even field, 4. And one at the bottom, that is this portion is again in the odd field. So all these scanning lines, they are lying in between them, interlaced. So when the scanning takes place, the portion of the odd field and the even field, they're scanned by the electron beam in portions, and then they are combined together to form this picture frame. But here in progressive scanning, the scanning takes place at once, okay. But here in interlace scanning, the scanning takes place according to the odd and even demarcation of the scanning lines. Half it is done, okay. So here it is exactly the odd number of fields is equal to the even number of scanning lines exactly. So here just because of this portion, one extra 5, the extra scanning line is obtained, but actually the number of odd scanning lines and the even scanning lines, they are the same. It means there should be another scanning line here, 6, because they are exactly equal, half, okay. So there are two main TV systems that use interlace scanning, the NTSC and PL system. So NTSC is based on a system of 525 lines, 60 fields and 30 frames per second, okay. The frequency is 60 Hertz, okay. The repetition is 30 frames per second. And PAL or PAL, we can say, is based on a system of 625 lines, 50 fields and 25 frames per second at 50 Hertz. So some countries they use the NTSC system and some countries they use the PAL system. So this is about scanning. Next is synchronization. So synchronization is, we can see in the receiver side, there is a synchronization and detection circuit. So here you can understand this process as, you see in movies or anything, the synchronization between audio and video is very important, okay. when we see a character saying some dialogue, they're moving their lips, they record the audio later. So it should be in sync with each other. It means whatever the dialogues or lines the actor or actress he or she is speaking, according to the lip movement, the audio should match. If there is any mismatch, then the audio will come first. Either the audio will come first, then the lip movement will happen, or the lip movement will come first and then the audio will be audible to us. So that is not good. Synchronization means the lip movement and the audio, they should be exactly matched. So here also, at the time at which the scanning happens at the transmitter side, okay, the electron beam scans the image formed on the photosensitive plate of the camera tube. At the same time, the receiver should also present the scanned image and the image which is generated, the electrical equivalent converted into the actual image by the picture tube. So for this, the synchronization process is very important. So this is the process by which the horizontal and vertical sweeps of the electron beam at both the transmitter and the receiver side, okay, the scanning and synchronizing circuit at the transmitter side and the synchronization and the detection circuit, they should be, the two processes should be kept in step with each other, in sync with each other, okay. So for this, the separate synchronizing pulse signals are transmitted along with the video signal, and they are also called as timing pulses. So what happens that if there is any mismatch between the transmitter side and the receiver side, we may not get an image like this. It will be it will appear a little bit jumbled. Some pixels will arrive early and not in proper order, and some other pixels will arrive later which should have arrived early, so it will appear jumbled, okay. The pixels will be all over the place. We may not get a picture which we should have got, okay. It will appear slightly jumbled in case of lack of synchronization between transmitter and receiver circuit. So for this, various types of signals are sent to maintain the synchronization, which gives us a composite video signal. So the video signal which is sent from the transmitter and the receiver is not just the picture or the image frame. Along with it, various other signals are also transmitted, such as the horizontal and vertical synchronizing pulses. The horizontal is for the scanning lines and the vertical is for the fields in case of interlace scanning. These are the synchronizing pulses. Then we have the blanking pulses. The blanking pulses are used so that these retrace movements, this vertical retrace in case of interlace scanning, and these horizontal retraces, and also here the horizontal retraces, they can be made visible. For that, blanking pulses are used, okay. So it makes the path of the retrace of the electron beam invisible. So that is the job of the blanking pulse. Then comes the equalizing pulses. The equalizing pulses, they are transmitted before and after the synchronizing pulses, okay, to eliminate the difference between odd and even fields, okay. As you can see here, in case of interlace scanning, we have already discussed that the whole picture frame is divided into odd and even scanning lines, divided into two fields, the odd field and the even field. So the odd field contains odd number of scanning lines, the even field consists of even number of scanning lines. So in case there is any mismatch in the rate at which the scanning takes place for the odd number of lines and the even number of lines, for that the equalizing pulses are used, so that both the scanning takes place in step with each other, in sync with each other. So the synchronizing pulses, they look something like this, the horizontal or line synchronizing pulses, and the vertical synchronizing pulses, the field synchronizing pulses, they look something like this. and the equalizing pulses, they are simply a pulse train like this. The width of all the pulses are same, but here in the middle there is a slightly higher width. Why it happens like this we'll discuss in the transducer section. Okay, here just understand this much. So here we have discussed about the general principle of scanning and synchronization in TV transmitter and receiver. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics, instrumentation and communication engineering. Have a great day. Thank you very much.